Hi, my name is Susan Wang, and welcome to the short summary of our paper, Stochastic Gradient Estimation for Higher-Order Differentiable Rendering. Inverse rendering optimizes scene parameters, such as geometry, BRDFs, lights, by comparing renderers to target images. But there are some pain points about this. First, rendering equations has discontinuities and plateaus, so auto-differentiation delivers wrong or zero gradients in many places. For example, in this inverse rendering task, a mug needs to be rotated from left image to the right one, moving through the parameter space. When the handle is obstructed by the mug, the loss won't change, and an accurate gradient will give 0, leading to a halt. In addition to the plateaus, almost all prior work experiments with first-order gradients, because they are easy to compute and readily available in many autodiff frameworks. However, they are direction only. Without curvature, they take many wasteful and small steps. Previous work on plateau-reduced differentiable path tracing by Fisher and Ratio uses a convolution trick that reduces plateaus and works with black box functions, but it uses first-order method. Our work explores the possibility to estimate a second-order gradient for faster, more robust optimization that also eliminates plateaus and discontinuities. Our key idea is inspired by PIDPT. The rendering equation for the light leaving a non-luminous point x in direction WO, given the scene parameters theta, is defined as an integration of radians r over all incoming light directions. This is convolved by a Gaussian kernel to smooth out the plateaus. The convolution is then differentiated with the differential operator d in order to get gradient information. This is hard to sample for convolution due to the complex landscape of the rendering equation, but with the smoothing convolution, we can use the Leibniz integral rule to move the differential operator inside the integration, acting directly on the Gaussian kernel. This is equivalent to convolving with the differentiated kernel. Depending on the differential operator, we have a first-order kernel and a second-order kernel. For first orders, we have gradient. For second orders, we have Hessians. However, computing Hessians directly would be costly, and most second-order algorithms uses Hessians to complement the descent direction. So another second-order kernel would be the Hessian vector product. Since convolution is continuous, we need to sample for it for all three cases. For the gradient of the Gaussian kernel, it is positivized and normalized similar to PIDPT. It is separable, so we can treat each dimension individually, while marginalizing the other dimensions when sampling for a single component dimension. The Hessian of the Gaussian kernel is divided into the diagonal and non-diagonal parts. Due to the separability of Gaussians, the non-diagonal part can be thought of as a Gaussian kernel where two differentiated directions are the gradients of the 1D Gaussian, and others remain the same. For the diagonal part, we derive another positivized and normalized PDF, then integrate to get the CDF. A lookup table is needed for sampling because there is no closed form solution to the inverse of the CDF. For the Hessian vector product case, we use the finite difference method to calculate the directional gradient of the gradient along the vector v. This is inspired by the fast Hessian multiplication by Perlmutter. One problem for this is that all dimensions of the Hessian need to be sampled. For example, a two-dimensional problem will require sampling 4 times and evaluating the function 4 times, which is costly. We instead used an aggregated sampling method, which samples the average of the distributions, reducing the number of evaluations needed. For second-order optimizers, we chose conjugate gradient method. One advantage of the conjugate gradient method is that with gradient descent, it only points towards the steepest descent at the local point, so it leads to zigzag line trajectory. The conjugate gradient helps by combining all the descent steps with similar directions into one conjugate direction. Hessian vector products are used during the line search, which matches our goal to make use of HVPs. Here we picked some qualitative results that test our method. One example of the task is to move a sphere that is outside the view to the correct position such that its shadows matches the reference. We compare our results to the state-of-the-art inverse renderer Mitsuba. We can see that Mitsuba doesn't converge because of the plateau. Comparing to the first-order predecessor PRGPT, our method is considerably fast in lower dimensions, and faster as initial convergence for high-dimensional inputs. In conclusion, we introduce an unbiased estimator for the second-order gradient information and uses the conjugate gradient method to utilize the information for inverse rendering. Following our previous work, our method achieves faster convergence speed, in addition to having the advantages of smoothing out plateaus and working with black box functions. There are still some limitations to our work. The aggregate sampling method adds variance in addition to the variance added from working with hashing and HVPs. Full hashings don't scale, so HVP plus conjugate gradient is preferred for larger parameter spaces. In addition, our work requires safeguards to avoid hashing divergence using methods such as trust region methods, which limits the effective step size. For more information, please check our project page or come to the poster session on Thursday.